Hey everybody, today we're going to be talking about continuity, and then we're going to go into some interesting concepts under continuity, and then finally we're going to go over intermediate value theorem. But before we get into that, I want to discuss this one question that I came across, and this is related to our previous video, which was on piecewise definition of a limit. So we're just going to go over this one question real quick. Okay. So we have limit x tending to 1 over x is equal to 1/2. This is what we want to prove. How do we proceed? We proceed by saying, x minus 2, x minus a is 2 here, is less than delta. And then we have f of x minus L is less than epsilon. F of x is my function 1 over x. L is my limit, which is 1/2. So 1 over x minus 1/2 is less than epsilon, which would imply, so this is my rough work, right, step 1, which would imply taking the LCM, that would give me 2 minus x over 2x is less than epsilon. I can separate the mod sign in the numerator and denominator, and I can make this 2 minus x, x minus 2, because they're the same thing. This is the difference, this distance from x to 2, right? I can switch. So I have this, right? And if you remember previously, like the way we show this is that we want to show that this value, x minus 2 over 2x, is less than some c times x minus 2. And then I can show this value, c times x minus 2, is less than epsilon. And then I can take my delta as epsilon over c, right? And send the c down there. All right, how do we do this? If you remember from the previous video, where we show that we take a random value, we take usually 1. So I say x minus 2 is less than 1 and is greater than my negative 1, right? X mod of x minus 2 is less than 1. This is how we write it, which would imply adding 2 to both sides. I get 1 is less than x is less than 3. And I have x minus 2 here, right, in this form that I have. But I want 1 over 2x, right? That's the thing. So how do I convert my x minus 2 into a form that translates into 1 over 2x? How do I do that? Okay, so then I find the reciprocal, and I find 1 over 1, which is 1, and 1 over x, and 3 turns to 1 over 3. However, when you find the reciprocal, you switch the signs. So here, it's less than equal to s. Here, it's going to be greater than equal to 1 over x. So this, right? And then I want 1 over 2x. So I multiply all 3 of these by 1/2. So I get 1 over 2 is greater than 1 over 2x is greater than 1 over 6. Now, when I convert this into a mod, I take the bigger value. So 1 over 2 is greater than 1 over 2x, right? This is the equation that I have, right? Now, if I multiply both the sides by mod of x minus 2, I'm going to get x minus 2 over 2x, right? Is less than x minus 2 times 1 over 2. So this is my c. I just found my c here, okay? So, all right, now I found my c. How do I write this out? So now I know that c is 1 over 2. So then if you remember correctly, this was going to be delta usually is epsilon over c, right? And c is 1 over 2, so epsilon over 1 over 2, which is what? Which is 2 times epsilon. Okay, so let's write this out now. This is our actual proof. This was our rough work, and now we write the actual proof. Okay, so we say that that epsilon is greater than 0, and delta is equal to the minimum of 1 and 2 times epsilon, right? 1 because we took that random 1, right? We wrote x minus 2 is mod of that is less than 1, from which we got minus 1 is less than x minus 2 is less than 1, right? So that's why the 1 and 2 epsilon from the previous thing that I showed you. And then I write, then if I have x minus 2 is less than 1, this, and now I proceed, right? This is less than 1. This, and this is what? Right? And this is just this. And this is just this. Right? I show this. My 1 over 2x is less than 1/2. And I know that x minus 2 is going to be less than this. Epsilon over c, which is 2 epsilon. Right? So multiplying both of these, I get multiplying 1 and 2, I get x minus 2 times over 2x, right, is less than 1/2 times 2 times epsilon, which is this, and this is just 1 over x minus 1/2 is less than epsilon. And this is the result that I wanted to prove, right? So this is our proof. Okay, good. Now let's start with continuity, and let's start with the definition of what it basically means. Okay, so what continuity basically means is that, you know, if I'm finding the limit of like some x approaching a, f of x, that should be equal to f of a. This is what continuity basically means. When I'm drawing the graph, right, what it basically means is that when I'm drawing the graph of a particular function, right, I should not lift my pen or pencil when I'm drawing the graph anywhere. If I don't do that, then the function is continuous, right? So this would mean that my left hand limit and my right hand limit are the same, right? Which means the limit would exist, and they have to be equal to f of a, right? The value that f takes at a. Let's look at an example, right? So I have this graph here, and this is what it looks like. Okay, so if you look at this graph, let's look at 3 points, right? This is point 1, this is point 2, and this here is point 3. Okay, so at point 1, the function does not exist, right? There's an empty circle here, which means that the function, this entire piecewise function that we just drew on the board, it's discontinuous. So the first condition is that f of a should exist, right? That's the first condition, where a is 1, so f of 1 should exist, right? All right, let's look at the other point. Let's look at 2, right? At x is equal to 2, what is happening? So at x is equal to 2, the function does exist, right? You see this black dot here in this empty circle, but you know the function does exist, because that's why we have this, you know, at x is equal to 2, the function does exist. However, the left hand limit and the right hand limit are not the same. The left hand limit at x is equal to 2 is going to be this value right here, this -1 or something, right? The y value is going to be around -1. And the right hand limit is going to be something positive, like around 5 or something. That's what it looks like. So for the function to be continuous, we see limit f of x when x is approaching a should exist, right? So ditto marks. So then if they, like, for this to happen, the left and the right hand limit should be the same. All right, let's look at the third point now. Third point, the left and the right hand limit are the same. The function does exist, right? I have this dot here. However, the limit, which is going to be this point, right? This y value at x is equal to 3. Both the left and right hand limit are this value right here, right? Let's call this 3, right? Both the left and right hand limit are 3. However, f of this 3, this value, is not this, it's this, right? Which is around, let's say, 7. So this is 7, while the limit is 3, which means that the third condition is limit x tending to a, f of x should be equal to f of a, right? So at 3, f of 3 should be x when x is approaching 3. For this function, they should be the same. However, they're not the same. So this function, this piecewise function that I just drew here, it's not going to be continuous at all 3 points. All right. Now there's another concept that emerges, which is continuity from the left and right hand side. So what that means is that if you, like, I just wrote the definition as this, right? X tending to a, f of x should be equal to f of a. This is the definition of continuity. This is the condition that we need to fulfill in order for the function to be continuous at a, right? For a function to be continuous from the right hand side, this condition has to be true. So this means that the continuous from right, and then this limit x tending to a minus f of x is equal to f of a is simply continuous from left, right? Let's look at an example of when this would happen, right? So how many of you remember the greatest integer function that we talked about in our previous videos? So the greatest integer function is written as this, right? A lot of people write it this way. And if you remember, they're drawn like this, right? It's a step-by-step function, right? This is what it looks like, which basically tells me that if I take a value like, if I plug in for this function f of x, if I plug in 2.1, I'm gonna get 2. If I plug in 5.7, I'm gonna get 5, the left-hand integer. So if I plug in negative 1.2, the left of that, if you imagine the number line, it's gonna be negative 2, right? So that's what it basically does, right? That's why we have these steps here. So if you like pick any random point, right? Let's just pick this point. Let's say this is x is equal to 2, right? So for this function, we see that the left-hand limit, what's that going to be? 2 minus of f of x. This value right here is what? This value is going to be 1, right? Because if you have something, if you remember, if you think back to what limits are, left-hand limit is going to be something like, for 2, 1.99999, right? If you plug that value in for this function, you're going to get 1, right? However, for the right-hand limit, if you have something like 2.00001, are like super close to 2, right? But from the right-hand side, that's going to be 2. And what's f of 2? Like what do you get when you literally plug in 2 here? So f of 2 is 2, right? So this means that this function, the greatest integer function, it's going to be continuous from the right? Because right hand side, right? Because both those values are going to be 2. However, if you look at the continuity from the left, it's going to be 1. But these are true for integer values. If you have something like 1.5, right? For that, 1.5, when you plug that in here, that's going to give you, if you plug in 1.5, f of 1.5 is 1, right? Let's look at that as well. So f of 1.5 is 1. The left-hand limit, let's just think what it would be, right? If it's here, left-hand limit would be something like 1.499999. Plug that in for the function, you're gonna get 1. The right-hand limit is gonna be something like 1.50000001. Plug that in, you're gonna get 1. So this case that it's continuous from the right, just from the right-hand side, that's true only at integer values, 2, 3, 4, -3, -2, right? However, for non-integer values like 1.5, there's no problem. It's just continuous at any non-integer value. So that's what we learned. That's the whole point of continuity from the left and right. Then there's another concept that comes into light, and that's continuity in an interval. So let's say I am given this function f of x is equal to 1 minus root 1 minus x squared. And I'm asked if this function is continuous in the interval -1 to 1, right? So how do I do that? The way you solve this is that you write limit x tending to a, right? Where you say that a lies between -1 and 1, right? This is the condition you impose, and then you plug in the value, so you're going to get 1 minus a squared, and this is basically limit x, right? Then you plug in the values, and you're going to get ultimately 1 minus root 1 minus a squared, which is the same as f of a. When you plug in a, you're just going to get this, which means that the limit, and when a is between -1 and 1, it's just going to be f of a, right? You can test the left and right hand limit. I'm not going to get into that. So if you want to test the right and left hand limit for -1, the right hand limit for -1, so on and so forth, you can test that yourself, and you're just going to find that they're all going to be this function. So that means that the function f of x is continuous in this interval -1 to 1. All right. Now we're going to get into something that we've looked before, which is basically, if you guys remember limit laws, we said that if f, right, this is something that we wrote in limit laws. Limit x tending to a, f plus g can be written as limit x tending to a f plus limit x tending to a g. Right? These are the limit laws. We can kind of use those in when we're talking about continuity. How? Well, we can say that, if we know that f is continuous, g is continuous. I'm just going to write CONT for saving time. So if we know these two are continuous, then the function f plus g is also going to be continuous. F minus g, also continuous. F times g, continuous. F divided by g, continuous, but when g does not equal to 0, right? And also c times f is continuous as well. If you remember, c is the scalar, and we've covered that in the previous video, so do look into that as well. C is only like 1/2 times this function f, that is also continuous, if I know f and g are both continuous. Right, this is pretty straightforward. These are the theorems that you're gonna see. Also, there's another interesting thing that we can use, and I'm pretty sure that you guys are familiar with the concept of domains, right? Every function has a domain, it has a range, it has a codomain. Domains are like all the x, values that x can take for the function to be, a function defined on its domain. So if a function is defined on R, which is all real numbers, then something like root x, right? If you have f of x is equal to root x, the domain would be anything greater than 0, right? Because anything greater than equal to 0, you can plug in 0 here, but you cannot plug in anything less than 0. -1, that's going to be a complex number, which is not real, so we can't. So that's not. So the domain for this function is x is greater than 0, right? Okay, so this is what basically domain means, right? So there's this thing that we say when we're discussing continuity, which is basically, I have these different kinds of functions that we've looked at, right? So first we have the inverse trigonometric functions, right? Then logarithmic functions. Then we've also looked at algebraic functions, which are of 3 types, broadly speaking: polynomial, rational, and root. Polynomials like 2x squared plus 3. Rational is like 3x plus 7 divided by 2x plus 8. Root is something like root 2x plus 5, right? These are the 3, but these are all algebraic. Then there's trigonometric functions: sine, cosine, tan, and then finally exponential, which involve the e to the x, right? This function, e to the x, e to the 5x, e to the 7x. Log is like our natural log, and inverse trigonometric is sine inverse x or something, right? So these are basically the different kinds of functions that we have, and there's this theorem that we can use that says that, these functions, all of them, which are basically all the different kinds of functions you're going to cover in your syllabus, they're going to be continuous in their domains. So log x, right? Let's just talk about log x. Log x is defined only when x is greater than 0, right? X cannot be 0. X has to be greater than 0 for it to be defined in the real space. So the logarithmic function is going to be continuous for logarithmic functions like ln x, right? This ln x is going to be continuous for all x is greater than 0. So this is a really interesting and really strong theorem that you have at your disposal when you're solving questions. So for all these different functions, we can say that they're going to be continuous wherever their domain is defined. Okay, let's get into a question now. Let's look at the different kind of questions you're going to be asked. Let's say I have this function here, f of x is equal to ln x, right, plus tan inverse x divided by x squared minus 1. So this function f of x is a combination of 3 different functions. The first one, log, right? If you remember the different functions that we covered. Tan inverse is inverse. And x squared minus 1 is polynomial, right? Algebraic and under algebraic, it's polynomial. Alright, so ln of x is defined for x is greater than 0. Tan of x is defined in all r, right? In all my negative infinity to infinity, I can plug in whatever value I want for x. X squared minus 1 separately is defined for all x, right? So that's also r. Which means that my combined domain, for instance, is going to be positive r. So that's going to be 0 to infinity. However, one thing that you need to understand is that this function as a whole is not defined at x is equal to 1, right? When you have x is equal to 1, you're going to get 1 minus 1 in the denominator, which is 0, which means that the function is not defined there. So we need to take 1 out. So if you're asked, where is this function, f of x, continuous? You're simply going to write 0 to 1, union 1 to infinity, right? Or you can write, you can use or as well. So then this function is defined for, or actually you can write f is continuous, C-O-N-T, for 0 is less than x is less than 1, and also for x is greater than 1. Right? So yeah, that's how you solve this kind of question. Alright, then there's something else, right? There's composite functions that I don't know if you guys have learned about yet, but it's basically when you plug in, we're going to go into an example, but basically it's that if you can write something like g or f of g of x. And I'm pretty sure if you guys covered functions, this is one of the types of function you're going to cover. So for this, what you basically say is that, let's say g is continuous at a, and I know that f is continuous at g of a, right, the value that g function takes at a, then I know that f of g of x is continuous at a. What does that mean? This is the theorem that you talk about when you're which connects continuity with composite functions. If g is continuous at a, f is continuous at g of a, then f of g of x, which is the composite function, is going to be continuous at a. Let's look at an example. I have ln of 1 plus cosine of x. Right, this is a composite function where f is ln of x and g is 1 plus cosine of x. So f of gx is ln of, I put that in for x, 1 plus cosine of x. This is a composite function, right? A simple textbook composite function. So if I'm asked what is the, where is this function continuous? I'm just going to say, oh, for ln of x, I know that x has to be greater than 0. But here, my x is basically 1 plus cosine of x, right? That's basically the relation that I have. So this function is going to be continuous for 1 plus cosine of x is greater than 0. X cosine of x is greater than 1, negative 1, right? And then that means that x is greater than cosine of negative 1. So then this would give you a bunch of values in pi, and then that's your solution. So you're going to say that for all values where cosine of x is greater than minus 1, this function is going to be continuous. Alright, so after that, we're just going to get into the final part of this video, which is the intermediate value theorem. And the intermediate value theorem is, again, a really strong theorem, and it's straightforward too, actually. So you say that, say I have this graph. It's always easy to explain a white graph, where I have this f of a and b on the x-axis, and I have this continuous function that goes, from wherever to wherever, and I say that in this bracket, a to b, in this interval a b square brackets, I know this function is continuous. Now what I can say is that, this is the value this function is gonna take, right? This is f of a, and this is f of b. So if I say that there's some n between f of a and f of b, right? Let's say this is an n that is here, right? This value n exists between f of a and f of b, then I can say that there is going to be a c for which f of c is equal to n. Because the function is continuous, I know there's no gaps, there are no breaks or anything, and I know that if f of a and f of b are like, it's a continuous function from a to b, then I know that, and of course, f of a does not equal to f of b, right? These cannot be the same, right? A does not equal to b. That's like a condition, right? So I can say that there's going to be a c between a and b for which this n value is going to be obtained, right? So what kind of questions can you be asked about from the perspective of an intermediate value theorem? So this is actually pretty straightforward, right? F of a and f of b, and I'm saying that there's going to be an n between those two. Then there's going to be a c on my x-axis for which when I plug in the c for my function f, I'm going to get that n, right? And that c is going to be between a and b, right, on the x-axis. So if I'm asked, I have this equation 4x cubed minus 6x squared plus 3 of x minus 2 is equal to 0. I have this equation. And if I'm asked, can you prove that there's going to be a root to the equation between 1 and 2? Right. How do I do this? All right, I plug in this is f of x, right? Let's assume this is f of x. And I find f of 1, which gives me 4 minus 6 plus 3 minus 2, which is 4 minus 6 is negative 2, plus 3 is 1, minus 2 is negative 1. And f of 2 is 4 times 8, which is 32. Negative 6 times 4 is 24. 3 times 2 is 6, minus 2, which is 32 minus 24 is going to be 8, plus 6 is 14, minus 2 is 12. So negative 1 and 12, right? So I'm told, I know that this function, f of x, is a polynomial function. This is an algebraic function, which means that it's going to be continuous for its domain. And I know that the domain for this function is R, so it's going to be continuous everywhere. So I have to tell, right, I'm asked that, can I prove that this function is going to be, this is going to have a 0, right, a root between 1 and 2? Yes, I can say that, because f of 1 is negative 1, and f of 2 is 12. So 0, that lies between negative 1 and 12, right, obviously, right, which is basically f of 1 is less than this value, n is less than f of 2, right? I know this. And I know that, what I can say is that this value is 0. Using the intermediate value theorem, I can say that there's going to be a c, there exists a c, this is a symbol for there exists an opposite capitalized e. There exists a c between in AB, right, which is less than, let me just write this, A is less than C is less than B. That tells us that f of c is equal to it. So we know that there's going to be a 0 between 1 and 2. There's going to be a value 1.7, 1.8, I don't know what it is. But there's going to be a value between 1 and 2, for which, when I plug that value in for this function, I'm going to get a 0. So that's it. That's all we're going to talk about in this video, which is about continuity. Next video, we're going to get into derivatives and differentiation, which is like super interesting. And yeah, I'll see you guys next time.